Hello everybody, we're going to be talking about Newton's third law of motion. This is a law that you've definitely been taught before at some point, may have been a while, but you've heard the definition before. For every action there's an equal and opposite reaction, and we like to replace action and reaction with force. So for every force there is an equal and opposite force. We refer to these forces as action-reaction pairs, or Newton's third law pairs. So let's go through an example. So let's say we have a box that is on the ground, and we have somebody who is pushing on the box, we'll say to the left. So here's this person, and they are pushing on the box, very long arms. Let's see, so basically what we're going to do, I'm going to draw each of the action-reaction forces in a different color. And basically it's just you push on something, it pushes on you. Alright, that's the idea of an action-reaction. The action is you push on something. The reaction is that something pushes back on you. And the force involved is equal and opposite direction. Alright, so let's start with the obvious one, the push force. So here I will draw the push force. Alright, and the reaction is that the box pushes back on the person. Okay, so there is a push force by the person on the box. Alright, and then the reaction force is the push force of the box on the person. It is equal in magnitude, opposite in direction. Alright, let's talk about some other forces going on here. You might say, well, is there friction? Yes, let's talk about friction. So where does friction act? It acts between the object and the surface. So which direction is friction acting? Well, it always acts opposite the direction of motion. So we say, alright, I'll start right here, and we'll say friction is acting this way. Alright, there's a force of friction, and that is an action force. And what is the other force? What is the other one that's opposing it? Well, it's pushing on what? The box is rubbing up against the ground. So the ground is supplying friction, and the other force is going the other way, and that is the box pushing on the ground. Right? The box is supplying a force trying to make the ground move to the left, and the friction from the ground is making the box accelerate to the right. But you put them together and they are equal and opposite. So it's the box acting on the ground acting on the box. Okay? Let's look at one more. There is a couple more we could say. There is the ground acting on the person, and the person acting on the ground. Alright? So the person is supplying a force to the ground. In what direction? Well, if you think about it, when you walk, you try and push the ground backwards, right? And then the ground actually helps propel you forwards. And I'm going to kind of overlap here now, but alright? So there's three sets of action-reaction forces that we're looking at here. We have the person pushing on the box pushing on the person. We have the ground pushing on the box pushing on the ground. That's in blue. And then we have the person's foot, I guess you could say, or feet, pushing on the ground backwards, and the ground actually is pushing the person forward. Alright? Now, of course, all that happens, especially the blue and the yellow, because of friction, right? But those are the action-reaction forces. Now, how does this apply to calculations? Alright? Well, and this sometimes doesn't make a whole lot of sense, because I get students that will ask, well, if the forces are equal, how can we explain the difference in the reaction of both, right? Well, let's take the example of, I'll talk about one example first, but the example of a fly being squished by a car. All right, car's driving down the road at some speed, and the fly, we'll say, is hovering, and all of a sudden, the car hits the fly, boom. What happens? Well, there is a collision. The force applied to the bug is the same as the force applied to the car. All right, what's the difference? Well, it's mass. Because the mass of the bug is so small and the mass of the car is so large, we don't notice a difference in the car. But of course, the bug notices the difference because he ends up splattered against your windshield. Okay, so that's one example. Let's think about another one here. If you are jumping off a cliff, okay, maybe you're jumping off into some water. Okay, so you jump off and you are falling. Now, we know that there is a force of gravity. There is a force of gravity, and that is pulling you down, and that is equal to your weight. It is mass times acceleration of gravity. We know that. Now, according to the third law, there has to be an equal and opposite force. So gravity, the earth, is pulling you down. So therefore, according to the third law, you have to be supplying a force to the earth. Okay, that's a little strange. Now, this would be, I'll draw this underneath, but there has to be a force of you pulling the earth up. All right, so let me erase that and rewrite it as this is the force of the person on the earth. Or I'm sorry, let's mess that one up. It is the force of the earth on the person. Okay, so the earth is pulling the person down. This reaction force is you, the person, pulling the earth back up towards you. All right, so this is the force of the person on the earth. Let me put their vector symbol up there. Now, let's think about this for a second. The force that you are being pulled down to earth is the same as the force that you are applying to the earth to pull back up. Okay, well, why doesn't the earth move? Because of its mass. All right, we know that based on Newton's second law, F net equals m times a, that objects accelerate based on their mass if we assume a constant force. So we know there's a constant force of gravity near the Earth's surface based on the acceleration of gravity. And if the mass of the two objects are vastly different, but the force is the same, their accelerations, the reaction to that force will be very, very, very different. So I hope that makes some sense. Let's look at an example with some numbers. Okay, so let's say we have, let's look at a situation. This is kind of a classic situation that is looked at for the third law. So let's say there is a cannon that's going to fire a cannonball, okay? And the cannon has a mass of about 100 kilograms, and the cannonball has a mass of about 10 kilograms. All right, so when the cannon is fired, there's a certain amount of force that it propels the cannonball with. Now, according to the third law, the force on the cannon feels a force, I'll say this way, and the cannonball feels a force this way. And they are the same force. They are equal in magnitude, opposite in direction. Okay? So, if we wanted to find out what is the acceleration of each of the objects. So we say, all right, well, we know that our second law tells us the net force equals mass times acceleration, and we do that for each object. All right, and for each one, then we solve for acceleration, and we have F net over mass. And as you can see from this equation, of course, the accelerations are going to be drastically different due to the mass. So if we say that a force of 100 newtons is created because of the firing of the cannon, then we're gonna have different accelerations. So we have 100 newtons divided by 100 kilograms, and acceleration of the cannon itself is going to be 1 meter per second squared to the left. And the acceleration for the cannonball is going to be 100 newtons divided by 10 kilograms, and that is going to be equal to 10 meters per second squared to the right. Okay, so here is that acceleration, and here is that acceleration. And as you can see, it's going to absolutely be totally dependent on the mass, and that is always how this works. Now, one thing to mention, be careful. You cannot say that these forces cancel out. And the reason is, even though they are equal in magnitude and opposite in direction, they do not cancel out because they act on two objects. Forces only cancel out when they are equal and opposite and they act on the same object. These do not act on the same object, so it is not correct to say that they cancel out. All right, that is a quick run through of Newton's third law. Hopefully it helped, and we'll catch you later.